Annette Caenen is a civil engineer and also holds a Ph.D. in biomedical engineering. She's going to explain her current research interests.
Okay. So hello everyone, I'm Annette Caenen and I will be talking today about cardiac shear wave elastography. So what kind of research am I doing? So we're actually combining biomechanics and ultrasound knowledge. So I'm actually active in 3 labs. So one is here in Ghent, where they are specialized in computational biomechanics. And then I'm working also together with 2 ultrasound labs at clinical centers, and those are in Rotterdam and in Leuven. So what is actually the clinical goal actually of this research is that heart failure is common worldwide. So about 1 to 2% of people have heart failure, and these patient numbers are continue to increase. Now, the heart failure survival rates remain poor. So actually 70 to 45% of the patients admitted to the hospital with heart failure will die within 1 year, and the majority will even die within 5 years. So therefore, it's actually very important that we have techniques available to guide treatment, but also patient follow-up. So now we have actually several techniques available where we can image the anatomy of the heart, the hemodynamics of the heart, also valvular function. And we do have some techniques available for ventricular function, but there it's still a bit poor. So what is the golden standard now? To evaluate ventricular functions, and those are actually pressure volume loops, where a conductance catheter is actually entered through the groin, and then it's progressed into the heart. And then we can actually measure pressure and volume and function of time, as you can see here in these curves. And then when we plot the pressure and the volume and function of each other, we get the well-known pressure volume loops. Of course, the main disadvantage of this technique is that it's invasive, and we cannot have a regional assessment of the heart if there's a local fibrosis present. But of course, the advantages are that we can assess both systolic and diastolic function, and we get a more global assessment over the complete cardiac cycle. Now, there are some non-invasive alternatives available to evaluate cardiac function. So first, for systolic function evaluation, there's a well-known parameter ejection fraction, which measures actually the amount of blood pumped out of the ventricle compared to the total amount of blood in the ventricle. And a reduced ejection fraction has been associated with cardiac dysfunction. And we can easily measure this parameter using ultrasound, as you can see here on the right-hand side. Now, of course, the advantage is that it's non-invasive, and we do have a global assessment of systolic function. However, the disadvantage is that the reproducibility is not always as good. Then for diastolic function evaluation, it's a bit more complex because there are several guidelines available concerning the measurement of multiple parameters. As you can see here, a list. And then based on these parameters, there is actually a classification, a normal, mild, moderate, or severe diastolic dysfunction. Now, of course, it's very difficult to get reliable and consistent findings from individual measurements, and this can result then in an incorrect classification. So therefore, there's a need for new techniques to assess cardiac function. So as we can see, the heart actually contracts and relaxes alternatively, and this can actually be compared like with a skeletal muscle. So there's continuous actually contraction and relaxation of the muscle, and during this contraction and relaxation, we get actually changes in muscle stiffness. And therefore, we're actually interested whether we can measure cardiac stiffness in order to evaluate cardiac function. And therefore, we're especially interested in ultrasound techniques, as these are non-invasive, they're widely available, they're low cost, and they are radiation-free. So therefore, there's a specific group actually of techniques called elastography, which measure tissue stiffness. And this is actually based on the old technique of palpation, as you can see here. And this has been an important diagnostic tool in the clinic for centuries. So if you have a specific tissue with a tissue stiffness E, and we apply a certain force on this tissue, then we get a specific, a specific strain, as a result from the compression of the tissue. When we have a low compression, the tissue stiffness is high, and when we have a high compression, we have a low tissue stiffness. So here you can see some values for various organs, and we can see, for example, for healthy breast has a stiffness of about 1000 Pascal. And what is interesting is, of course, that when a disease is present, we can see that the stiffness increases. So when there is a breast tumor, the stiffness can range from 900 to about 2500 Pascal. So this is one of the interesting things of this technique. And then, of course, with palpation, we have the disadvantage that we can only palpate very shallow, so only the first 2 centimeters, and it can be, of course, a bit painful for the patient, and it's very subjective. Now, we want to extend palpation beyond the physical touch. So therefore, instead of actually manual compressing it, we're using an ultrasound probe to compress it. So here you can see on the right-hand side a pre-compression and post-compression. And when we compare actually both images, we can obtain a strain image. And in the strain image, we have again the same principle where a low compression means a high stiffness and a high compression indicates a low stiffness. So now what is the added value of the strain image compared to a conventional B-mode? So for example, here you can see the B-modes of 2 patients. And we can see that there's actually in both patients, there's a hypoechoic region present, which is indicated with the letter A. Now, of course, the B-modes look very similar, and the question is which B-mode image now represents a malignant or a benign breast lesion. Now, when we look at the strain image of patient 1, and we look actually in the strain image at the same location as where the hypoechoic region is present, which is indicated with the red circle, you can actually see that the strain is green, so it's on average. And if you compare it to, for example, where the B is indicated, or to the rest of actually of our strain image, we can see that it's in the similar range. So therefore, this is rather representative of a benign lesion. Now for patient 2, when we try to situate again actually our hypoechoic lesion in the strain image, we can see that it has a blue color, so it's very hard compared actually to the surrounding tissue, and therefore it's rather representative of a malignant lesion. So many previous studies have actually shown that ultrasound elastography can help to differentiate malignant from benign breast lesions and actually reduce the amount of false positive biopsy findings. Now, of course, in this specific work, we want to extend palpation a bit even further than beyond physical touch. And instead of compression with the probe, we will actually apply a remote palpation. So actually by emitting a high intensity focused ultrasound beam inside the tissue, we can also actually palpate remotely. And this is actually the technique called Shearer Velostography, and you can compare it actually to a mini earthquake, which is applied to the body. And we can see here the earthquake epicenters, and then we can see that waves start to travel originating from this earthquake epicenter. Now, of course, there are actually 2 kinds of body waves, where we can, so one is well known, the longitudinal waves, where we can see that the deformation of the medium, so the particle motion is in the same direction as the wave propagation direction. Now, of course, the propagation speed here is linked actually to the bulk modulus of the material. Then second of all, we have the transversal or the shear waves, where the particle motion is actually perpendicular to the direction of the wave propagation. And there the propagation speed is linked actually to the shear modulus, so the way that tissue resists to shear. Now we're specifically interested in shear waves because the technique is called Shear Velostography. And why is this? So if we look now at various values actually for different tissues, for example, for the bulk moduli, we can see that the range of the bulk modulus is not that big, and the speed varies between 1,490 and 1,540 meters per second. Now for shear waves, we can see that the range is much broader, and actually that the typical speed is between 0 to 10 meters per second. So why do we want to use shear waves? Is first, we have a larger sensitivity, as you can see from this graph, based when we discriminate tissue based on shear modulus instead of bulk modulus. And then second is more a technical limitation or practical consideration, is of course if you need to image shear waves, we need a much lower frame rate than when we want to image longitudinal waves. And actually this still, of course, as shear waves travel with a few meters per second, up to 10 meters per second, we still need a frame rate of up to a few kilohertz in order to be able to image this propagating shear wave. And so therefore, when we in the past, or traditional ultrasound imaging is actually made up of a line-by-line acquisition. So we emit focus beams, and then we get actually an image reconstruction, which happens line by line, as you can see here. So the advantages, of course, of this is that we have a high image quality, but of course the frame rate is only tens of hertz. Now, high frame rate imaging has only been possible since the 2000s because of the advent of the GPUs and the multi-core CPUs. And then actually, instead of emitting a focus beam, we're actually emitting all or exciting all piezoelectric elements of the transducer at once. And this way we can actually create or image also at once, but you can see that the image quality is much lower, of course, than that of when in traditional ultrasound imaging. But the advantage is that we can have a frame rate of up to thousands of hertz. And there are actually some techniques available to ameliorate the image quality in high frame rate imaging, but I will not go deeper into detail about this. Now, of course, when we look back to Shearer Velostography, so what is this technique? There are actually basically 3 steps. So the first step is our mechanical excitation, and this can be done by applying a high intensity ultrasound beam, as I said before. But second of all, actually there are also natural shear waves present in the heart, because, for example, when the valve closes, we also get a wave which is excited and which travels along the cardiac wall. Then the second step is that we measure our tissue deformation, and therefore we need a high frame rate imaging technique. And then the last step is that we derive our stiffness based on the wave propagation that we measure in step 2. And then, you can also see this equation, which is shown at the right-hand side. And this is actually the link between our shear modulus, mu. Then we have our density, rho, and then there is the velocity of the wave, which is c. So there's actually a very easy equation, which has been applied in Shearer Velostography. But now the problem is, the assumptions that we actually assume for our shear wave propagation, are these also valid for the myocardium? Now, of course, when we want to apply this technique to the heart, there are multiple factors that will affect our shear wave speed. So, the technique has been mainly applied to liver and breast tissue, where the technique has proven to be successful. But of course, when we look at it from an engineering point of view, these tissues are actually pretty large. They're more or less isotropic, and we can consider them linear elastic. However, if we look at cardiac tissue, it's, first of all, it's thin, so it's bounded. It is anisotropic because there are myocardial fibers present, and it is hyperelastic or nonlinear. So what does this mean actually in terms of shear wave propagation speed? So first, when we look at the geometry, so here you can see a typical shear wave propagation. So we can see that a shear wave is generated actually in the center of this animation, and then 2 shear waves are actually propagating, one to the left and one to the right. Now for cardiac tissue, of course, you can see that there actually are that's a bounded medium, so it's more like a plate. And you can see again that a shear wave is generated in the center, and that 2 shear waves are actually now propagating, one to the left again and one to the right. But that the propagation is way more complex, because the shear wave will start to interact with the boundaries. So the wave energy will get reflected, and we get mode conversions, and the wave physics is completely different. Then second of all, the anisotropy. So when we have an isotropic medium, this means that actually the stiffness is the same in all directions. So we get a nice circular wave propagation because the wave propagation speed is actually independent of the direction. Now for an anisotropic medium, there we will get more an ellipsoidal wave propagation pattern in which actually the wave will propagate faster along the fiber and actually slower across the fiber orientation, as you can see in this animation. And then third of all, the material nonlinearity. So when we have a linear elastic medium, what does it mean? When we look at the shear wave propagation at two different stretch states, we can see that the shear wave propagation does not change, so we get the same shear wave speed value independent of the applied stretch. And when we measure along the stretch, and that the shear wave speed will decrease when we measure across the stretch. Now for the simulations, we can see in general that there is a good correspondence with that of the experiments. Now, of course, this behavior actually is similar to the behavior that we measured during uniaxial testing, as we can see here. And you can, when we actually look at the specific stretch state, we know that actually the slope of this curve represents the instantaneous stiffness at a specific stretch state. So we can see that the material actually becomes stiffer when we look at a higher stretch state, and that this actually is something different than when the intrinsic material parameters of the phantom material will change, because this will really lead to a different curve, as we can see here. And actually a similar behavior is present in the myocardium, as here we can see some biaxial mechanical tests of human myocardium, and we can see again this nice nonlinear behavior in terms of stress and stretch. Then second of all, we studied the effect of geometry on shear wave propagation. So first I will talk a bit more about the wave physics in such a material, because actually in large organs we can talk about a shear wave which is propagating in the medium. However, when we have thin-walled organs such as the heart, the waves get reflected and will interact actually with the boundaries, and the wave actually becomes guided along the structure. And therefore, this is called a lamp wave, as we can see here. And we can see that the particle motion is a bit different compared to that of the particle motion of a shear wave. So when do we have a shear wave and when do we have a lamp wave? It really depends on the thickness of the organ compared to the wavelength of the wave which is present. Now, these lamp waves have another interesting feature, which is actually wave dispersion. So actually, wave dispersion means that the frequencies in the wave will not all travel with the same speeds as is actually present for a pure shear wave. So here we can see that actually higher frequencies in the wave will travel with a higher speed than the lower frequencies in the wave. So here you can see an example movie of a non-dispersive wave, where the group velocity is actually equal to the phase velocity of the wave. Now when we have wave dispersion present, so we can see actually on the top movie that actually the wave actually becomes elongated, and that actually the frequencies in the wave will travel with different speeds, and then the group velocity is not equal to the phase velocity. And we can actually also see this phenomenon when we just look at a boat which travels in the water, and we can see actually when we look at the ripples of the wave, we can also see that wave dispersion is present in these ripples of the wave. So what is interesting, so before we had only two kinds of wave modes which were present, while now we have an infinite number of lamp wave modes which can be present. And these, the phase speed of these waves are actually dictated according to dispersion curves, which are plotted here. And what is most interesting one are the anti-symmetric modes. So we can see here on the right-hand side, on the top, you can see the anti-symmetric modes, which look more similar to a shear wave, as I have shown before. But there are also symmetric modes, which are here shown at the bottom, but these are normally not excited during Shearer Velostography. So we can, when we look at the blue curve, which is shown on the left-hand side, we can see that lower frequencies will actually travel with lower speed than actually higher frequencies in the wave. And when we look at actually for an unbounded medium, so a large medium, there will actually, the curve will just be simply a horizontal line because no wave dispersion is present. Now when we look actually, because there are two types of shear waves, as I told you before, so we have these natural shear waves, which are also called passive shear waves. These are very low frequent, and we can see that actually, they are actually really in the upward rising part of the curve, so meaning that the frequencies in this wave will really travel with a different velocity. Now when we look at the active shear waves, these are usually higher, these have a higher frequency context, and we can see as well that these are also present in the rising part of our curve. Now ideally, so actually what the people do in non-destructive material testing, because they use also these lamp waves to characterize plates, for example, what they do is actually they choose a frequency which is not in this rising part of the curve, because if you would just choose a frequency which is in the horizontal part, we would not observe this wave dispersion, and this makes life easier, of course. But with the cardiac Shearer Velostography, we do not have really a choice, so there is wave dispersion present. And now we studied actually the effect of the left ventricular geometry by again considering phantom experiments, and these were actually performed together with the Longitudinal Institute in Paris. So therefore we created a polyvinyl alcohol phantom, as you can see here in the center, and then we used the Explorer system there to perform Shearer Velostography measurements. So here you can see the example of such a shear wave propagation in our ventricle. So we can see that the velocities or the tissue velocities are superimposed on the B mode. And there we can see again that the shear wave propagation becomes more complex. So we get more rounded curves, and we can even see a wavefront shifting which is happening. Now when we actually extract or tissue velocities at one specific M mode line, as we can see here, and we plot them in function of time, we can see actually one nice line representing the propagation over shear wave in function of space and time. And we can actually easily fit a line to it in order to obtain a shear wave propagation speed. However, when we look at a different line, as you can see here in red, we can see that the shear wave is split. So actually the wave propagation is more complex, and it's not that easy to actually obtain a wave propagation speed. So therefore we use actually a different technique, and now instead of analyzing the group speed of the wave in the time domain, we're now also looking at the phase speed in the frequency domain. So therefore we take the 2D Fourier transform of or actual tissue velocity plot, as you can see here, and then we convert it actually into these dispersion curves that you have seen before. And now we can estimate our stiffness or shear wave propagation speed by fitting a model to the extracted curve. And when we do that, you can see here the results. So here you can see the estimated shear modulus. First, when we use standard processing, which is actually implemented in all ultrasound scanners. And you can see here also in gray the value which we obtain for mechanical testing. And we can see that there's a clear underestimation of the actual stiffness of the material of about 30%. Now, when we use the phase velocity analyzing, taking our geometry into account, we actually can improve our shear modulus estimate with, as you can see here, but there's still a slight overestimation of about 12% present. Then the third factor that I will discuss is the anisotropy. So therefore, we set up again some ex vivo myocardium experience in which we actually cut off the right ventricle, and we cut open actually the interventricular septum in order to obtain a rectangular slab of the left ventricular lateral free wall, as you can see here. And these were then actually clamped on both sides, submerged in water, and we can see here the probe on top of it. And then we investigated actually the effect of anisotropy by rotating our probe, and then we also investigated the effect of the material nonlinearity by gradually stretching our material. So here you can see the example of the shear wave propagation when we image along the stretching axis of our material. And we can clearly see when we look at our yellow front in this movie, we can see that it's transmurally, it's changing a lot, so it's very curved. Whereas when we look, for example, now at a probe angle of 90 degrees, which is actually perpendicular to our stretching direction, we can actually see that the wave propagation front is very straight, so there's not that much difference in wave propagation speeds throughout depth. So now our speed is actually not only dependent on depth, but also on the probe angle, as we can see here. And we can actually obtain a shear wave propagation map, as we can see here. And the pattern in this map actually represents our myocardial fiber architecture, because the myocardial fiber architecture is actually changing transmurally across depth. So it means that depending on which depth and which probe angle you will analyze, you will get a different wave propagation speed. So now we also applied uniaxial loading, and there when we increase our loading, we can see that our shear wave propagation speed increases, as we can see here. Then the next step was that we modeled, or we performed some complementary modeling of these experiments, where we used an Holzapfel-Ogden material model in order to model the myocardium. I will not completely explain all equations, but actually it basically contains a volumetric part, and then we have our deviatoric part, which are related to shape changes of the myocardium. And there we have multiple contributions, as we can see. So first term is actually the contribution of the matrix. Then the second two terms are actually the contribution of the myocyte fibers and the collagen struts in the sheets. And then there is still a last term, which is the relative shear contribution. And then we assumed a fiber orientation, which varied linearly from 50 degrees to minus 50 degrees, parallel to the cardiac wall, as we can see here. And then we can also see all parameters values that were assumed on the right-hand side. So now when you look at our simulations, we can actually see again the shear wave anisotropy. So we can clearly see in the epicardium that the shear wave is actually propagating at a different direction, or the directionality of the shear wave is different compared to that of the endocardium. And when we validate our results, so we applied also the 3 different stretch ratios as we did in our experiments, and we compared that to the results obtained of our simulations, and we can see that there's a pretty good correspondence. Of course, we do see that there are some differences in values, but this is because the simulations used a literature-based model and not the actual material model of our experiment was actually not determined. So this was just an assumption that we made. Now with these simulation results, we can actually also model shear wave propagation in the fibrotic heart. And you can see here that shear wave propagation looks completely different when the heart is much stiffer. Now when we compare our wave propagation patterns in a healthy and a fibrotic heart at 3 different depths. So here you can see on the left-hand side our shear wave propagation in the healthy heart. And we look now at the shear wave propagation in function of space and time at 3 different locations, as we can see here. And when we compare that to those of the fibrotic heart, we can make several observations. So we can see that the shear wave characteristics for the fibrotic heart, that the group speed is much higher than that of the healthy heart because it's more inclined, the yellow curve, as you can see. And then second of all, also it's more dispersive because it's more spread out, as you can see here. So the positive, or one of the encouraging findings here is that we do actually see an altered temporal shear wave characteristics in the fibrotic heart, meaning that Shearer Velostography is actually able to pick up changes in the heart. And then last of all, I will still talk a bit about the hemodynamics and the contractility of the heart and what the effect is on the shear wave propagation speed. And therefore, we actually used open chest PIC experiments, which were performed in collaboration with the Erasmus Medical Center. So here we can see the setup, where we first looked at these natural waves, which are naturally present in the heart. So therefore, we just image the heart in a parasternal long axis view, as you can see here. And then when the aortic valve or the mitral valve closes, we can see a wave actually which is traveling along the septum. as you can see here. And here you can, oh, the movie is suddenly much faster, but you do see a wave traveling, but the frame rate is much faster. Okay, then we also looked at waves which are generated by this active push that I've told you before. So we, in which you can compare the focus of the ultrasound beam to the epicenter of an earthquake. And then, second of all, we apply high frame rate imaging in order to image the two shear waves which are generated, and one is propagating to the left and the other one is propagating to the right. And this was then actually repeated 35 times across the cardiac cycle. And here you can see the example of such a shear wave propagation in the heart, where the white lines indicate the border of the interventricular septum. And we can clearly see that, again, two shear waves are generated in the center and each are propagating to an edge. Now, when we look at the results of active Shearer Velostography, so when we push to induce the shear waves, we can see that actually depending on when we analyze them in the cardiac cycle, that the shear wave speed is changing. So if we plot that in a curve, as you can see here, we can clearly see that there is a cyclic variation, and that the lower speeds correspond to the diastolic phase of the heart and the higher speeds correspond to the systolic phase of the heart. And even further in literature, it has been suggested that diastolic shear wave speed might be a measure for tissue stiffness. So this is something that we are interested in, of course. And second of all, that the systolic shear wave speed might be a measure for contractility. But this still needs to be figured out. Then now for natural shear waves, there it is a bit of the question now what and when are we now exactly measuring? Because mitral valve closure was is thought to represent anti-Systolic phase, and aortic valve closure is thought to represent end-systolic phase. But there's a lot of debate going on. So what we did is we actually measured both active and passive shear waves in the same shear wave acquisition. And then you can see here the shear wave speed as a function of time. And you can see the box plots. Those actually represent the shear wave speed measured for mitral and aortic valve closure. And what we can clearly see from this plot is that actually the timing of natural shear wave elastography is actually in between relaxation and contraction, because it's on the rising or in the decreasing curve of our active shear waves. So we can clearly see that the speed that we are measuring with mitral or aortic valve closure is actually when the heart is in between relaxation and contraction. And furthermore, second observation that we can make based on this figure is actually that the shear wave speeds correspond. If we would compare really at the exact same timing, even though there are actually a lot of differences in characteristics. Now, of course, each technique of active and natural or passive shear wave elastography has its advantage or disadvantage. So what is the advantage of natural or passive shear wave elastography is that it has a higher feasibility, because the tissue motion that we can see on the image is actually much larger, so it has a larger amplitude, so it's easier to track. And second of all, it's much easier to implement in current clinical systems, because we don't need an active push to induce shear wave. So with other words, we are acoustically safe. Now for active shear wave elastography, the main advantages there is, of course, that we can manipulate the temporal and spatial characteristics of our source, and thus also of the shear waves. And then second of all, we can track shear wave speeds throughout the complete cardiac cycle. So we're still a bit debating now what do we measure with one technique and what with the other. And we're thinking that they maybe can provide complementary information. So now to conclude, so I gave you a bit more of a basic talk about shear wave elastography with all its challenges, but it's also good to know, I think, that this technique is applied or is still in a research phase in the clinic. So there are multiple clinical studies ongoing, and they have shown promising results for shear wave elastography, as you can see here in this table. But it's still, all published researchers are very recent, and it's still all in development. So yeah, what can we conclude from this lecture is a bit that a pure shear wave is actually not excited in cardiac Shearer Velostography, which complicates the interpretation of our results. But it's important to realize that clinical studies are ongoing and that they do demonstrate an added value of Shearer Velostography. And this is also very good to have that we can establish reference values for healthy people, but also people with amyloidosis or hypertrophic cardiomyopathy and so on. Then in this work we developed several models and we performed several experiments in order to better understand actually what we are exactly imaging. And some ongoing and future work is that we're comparing shear wave metrics together with pressure volume derived metrics and seeing what the exact relation is between the two. And then second of all, we're also working on a global left ventricular model where we incorporate realistically the cardiac biomechanics and the shear wave mechanics. Okay, yeah, that was it. So thank you for your attention.